depth diving into kind of a lot of the extra hardening you can do and things like that. So we'll have more time at the end to talk and socialize and things like that. So my name is Liam, and this is going to be a short exploration of Kubernetes. All right, so we're going to start with talking about cloud native again. Go back to the beginning. So what does it mean to structure your application so it's cloud native? The general idea here is we're switching from a paradigm of you're spinning up your own servers, you're buying the hardware, and you're setting it up locally in your office or in a warehouse somewhere. And instead, we're going to utilize the existing infrastructure that's out there provided to us through various cloud platforms. Infrastructure as a service, I'm sure you're familiar with this term. And so different cloud providers, examples, AWS, GCP, Azure, and they all nowadays support their own internal Docker registry. So assuming that you've built your application using Docker, you have the images already set up, you can push these to the registries that are up on these various cloud providers, and then you'll be able to access them as you're deploying them on other services. And you also want to be cloud agnostic. The idea that you're not tied to a specific company, like you don't have to spin up your application on Azure or GCP, but then you can move it around potentially if there, for some reason you need to. All right, so when does Kubernetes come into the picture? When you're graduating from a single machine. So when we were talking about Docker Compose is a great tool. It lets you very quickly prototype something locally. You can get everything connected and talking to each other very quickly. The issue is it doesn't really support what you need in order to have production systems on multiple machines distributed in a cloud provider somewhere. So when we want to move to that application to production, what happens? Like, why can't we just use something like Docker Compose? There are a lot of additional concerns that come up. And those concerns are all kind of encapsulated in this topic of orchestration. So orchestration is the automated configuration, coordination, and management of clustered compute resources and distributed applications. So it's basically the fact that it's the idea that you're going to have now several VMs. Maybe it's 2 VMs, maybe it's 100 plus VMs. And all of these different resources, you want to balance out where everything is going to get deployed. If I say I want to deploy one container locally, it's pretty obvious where I'm going to put it. I'm going to put it on the local machine. If I say I want to deploy one container in a cluster of things that are already running, how do we figure out where that needs to be deployed? If it needs to be deployed on multiple of these machines, or if you can just put, which machine do I put it on? Does it not matter? Can I put it on any of them? Typically, example tools that use this stuff historically are like Chef, Puppet, and Ansible. Kubernetes is kind of in here. Kubernetes is more dissimilar to these first three than any of these first three are to each other. Because it's kind of a different, it adds a whole new layer of abstraction. As opposed to just managing VMs, now you have this infrastructure that's specifically built for containers. So a big part of Kubernetes is the ecosystem. It's not just as simple as like with Docker, you're just dealing with this one kind of product. It's kind of self-contained. It's one package. You can download Docker for desktop and you just have Docker. You don't have to install anything else. Then you can just start pulling containers and building stuff. The way that Kubernetes kind of came into existence was over a few years of time. And during that time, there were many people trying to run stuff with it before it was really ready. And in order to do that, people were rolling a lot of their own solutions for the different layers in Kubernetes. So it's a little more complex to look at because there's just more different pieces within the different sections of Kubernetes where you can plug and play various different examples of stuff. And we'll get into that when we talk about like networking and even stuff like container runtimes, right? Like Kubernetes supports Rocket, it supports Docker. So already you're making decisions around, I need to have one computer or one container execution engine, but I can pick from several. All right, so we're going to go into the architecture. So how does Kubernetes handle this issue of managing a bunch of different containers running in production? Basically, what we have here is an example of these two planes that they're separated out into. We have the control plane, which kind of handles the actual all of the stuff that you would interact with directly, things like scheduling, things like authorizing the user, talking to the sort of set of master processes that are going to orchestrate running everything on these various different VMs. And then you also have the worker nodes, and these are where everything's going to be run. These are a lot simpler, but you have a lot more of them, obviously. Right? You're only going to have a handful of these master components, and then you're going to have hundreds of these nodes potentially, where you're running everything, and these are all where the majority of the work is being done. It's a lot of arrows going on here, so we're going to jump into more specifics around this stuff. So we're talking a little bit the control plane. The control plane is generally broken down into these, just a few different services. I'll be going back and forth between these, so you can kind of see some of these things here. The API server is just a server that's running so that you can communicate with the master and tell it what you want it to do. You can spin up additional containers, you can create additional resources, you can ask about the cluster. You can say, what's my status, how many nodes do I have up, are any of my applications crashed, things like that. The scheduler is used to determine where new nodes should be run. So when you tell Kubernetes, I need 10 more of my web server, it needs to figure out which nodes to put these on, and then also, based off of various rules that you've added, maybe you have a hybrid cloud where certain applications can only be run on certain boxes. And so it needs to figure out, okay, of the available boxes that I'm allowed to run these on, where do I run these? And you can configure rules around that based on memory pressure, what's the healthiest box, what has the fewest containers on it. It could be that the fewest containers is the best way to decide where to put stuff. Or it could be that some of your containers are much larger than other containers, and so the fact that there are only a few on one box is not actually giving you any information about whether or not you should be running additional things there. We have the controller manager. This is a series of controllers that actually handle doing what the scheduler wants. So the scheduler looks at the current state of the world and figures out where things need to go, and the controller manager will actually execute that status and make sure that those things are actually spun up where they're supposed to be. And we also have etcd. etcd is a piece that's necessary for any clustered application. Is you have to have distributed state. So you need to have a way of keeping track of everything that's going on, even through failures. So etcd is a distributed key value store. So you always run it in an odd number of nodes. If you have the smallest number that you can run it at is 3, and 3 handles one failover, because you need 2 nodes of consensus. If there are 2 nodes that agree that this is what the state is, then that's what the state is. So if you want to be able to handle additional amounts of failover, you have to spin up more. So if you want to handle 2 failures, you have to have 5, and so on and so forth. And all of these things are typically deployed as highly available. So that means the difference between highly available and just parallelized is that something that's highly available will have multiple instances, but it won't necessarily be utilizing all of them. Those multiple instances are just there to make sure that if something goes down, you have another one to talk to. So it's not that you're running all of these things in parallel and using all of the existing infrastructure there, it's just that you have backups in case something goes down. And typically what that will mean for a cloud platform like GCP or AWS is that you're going to be running in multiple availability zones. So that if one of the availability zones goes down, as long as you have access to 2 other ones, then you can still run your cluster at least in those 2 zones. On the worker nodes, a lot less stuff going on, because mostly what's supposed to be going on the worker nodes is running your applications. The master nodes typically don't run any actual services, any of the containers. You're just running that kind of control layer to orchestrate everything. And then on the worker nodes, you want to keep this pretty slim. So we have the main 2 things are the kubelet agent. That's what actually talks to the API server. So you can think of it as kind of like a mini scheduler in a way. The master control plane will tell this node, you need to run 3 of these and 1 of these. And then the kubelet will handle actually making sure that there are 3 of those and 1 of those up on that singular node. So that's kind of a single machine concern. And then the proxy handles all the networking. So one of the cool things about Kubernetes is that it gives you an IP for every container that you're running. And all of the network traffic between nodes to make it kind of seamless so that containers don't need to be running on the same VM in order to be able to talk to each other. It means all the networking is going to the proxy. And then the last piece, of course, is you need some kind of container runtime. It's your choice what you want to choose. There's a lot of different supported things. Rocket is is one of the other ones aside from Docker, but Docker's obviously the biggest one. So once you have a container execution engine, now you can spin up containers in there and you can run all your applications. Yeah, I kind of already covered etcd, but I did have a slide for it just because I wanted to go into it a little more and talk about how it's important for any sort of clustered application to have some kind of data store so that the cluster as a whole, every component in there can reach out and figure out what the state of the world is. Typically what you'll find for the vast majority of older applications is that this is a zookeeper. It's a really common tool for the most common tool for this particular use case of like storing cluster state for different kinds of application architectures. Of course, Google wanted to build their own in Go because everything related to Kubernetes is in Go. So they implemented their own kind of version of that same type of application. It's called etcd. It stores the application state. It's the source of truth for the desired cluster state. We say desired cluster state because basically it's declarative, so it says what it wants it to be. It doesn't specify how to get there, but it says this is the state of the cluster that's supposed to be here. So then you can, from there, the application can figure out how to get there. And it also handles self-healing. So because it stores the application state, if something goes down, it knows that there's one less of that thing, and it knows that it needs to spin up another one somewhere else. And that kind of handles both self-healing and also updating configuration. So if you whether it's that something went down and needs to be spun up, or if it's that you decided you want more of that thing, it will look at etcd to figure that out. So now we can talk a little about the networking layer. And so here's an example of where Kubernetes differs a little in complexity from just a container runtime, and that now you have a lot of choices about what you want to use. There's a lot of different solutions for the networking layer. A lot of different companies have rolled their own because in the beginning Kubernetes didn't really ship with very viable networking implementations, so everybody was kind of rolling their own, and eventually now we have several solutions that all kind of work. One of the older ones, and then one of the sample ones that ships with a lot of like basic Kubernetes tutorials is Flannel. It's by CoreOS, which did a lot of the initial sort of development in the Kubernetes space. And it optimizes for simplicity. It's very easy to set up. It's not the most performant, but you can kind of just plug and play with it, which is nice. Something else that came out around the same time as Flannel is Calico, and it kind of handled the other end of that spectrum. If you don't care about simplicity, but you want to be able to have a highly customized example, or all kinds of ACLs, access control lists, different things like that Flannel just doesn't support, then you can use Calico. And then now something that's more relevant to, I think, modern applications is Envoy, which came out of Lyft, and that actually runs a separate kind of sidecar service on every worker node that works in tandem with the kube proxy to create an additional layer of networking. And Envoy is used by some of these other tools that work to create this idea of a service mesh. So a service mesh is a high throughput network architecture designed to support a large number of codependent microservices. It provides memory pressure-based load balancing, routing inbound requests to the healthiest instances. So this is something that's that comes out of once you realize, oh, Docker's great, I want to use this in production, and I start breaking all my monolithic applications into hundreds of little microservices. Suddenly there's a lot more complexity in something that was simple. Before it was annoying to deal with, having several teams working together on one application, they're kind of stepping on each other's toes. But now that you've split out the applications into several different projects, now you have all this extra overhead of the networking and the communication between these different services. And so it becomes necessary to add a higher level of complexity and tooling around networking and the architecture for where to send these requests. Things like, with a service mesh, you can specify even which containers or which services to talk to on a host by host basis. So you can say certain things are in a different different availability zone. Maybe don't talk to those ones, talk to the ones that are closer to you to get the best performance. But at the same time, should stuff in your own availability zone go down, in order to stay functional, you do actually want to have a fallback plan of being able to talk to those further away instances. So you can set the ruling around that through service mesh. And the service mesh, the things that provide service meshes are these three, the main ones that, let's see, lost it for a second, we'll be back. So you have these two actually are more similar, Consul and Istio. Consul is from HashiCorp. You guys are familiar with like the kind of thing that predated Docker almost immediately, which is Vagrant. It's a way of kind of creating these deterministic development environments. Consul is HashiCorp's tool that handles this network interface component. Istio is something that's come out more recently as well, and they both use Envoy in order to handle all their networking. And then Linkerd is another tool that's come out that does this, but it's only for Kubernetes. So these other two tools use Envoy because they want to be able to support other platforms. You don't have to use Kubernetes to create a service mesh. You don't have to use Kubernetes to run microservice architectures, but it's the most popular thing to do it with. And Linkerd is one that's is a solution to this that only works for Kubernetes, and because of that, it's more lightweight, but it's also not as flexible. All right, so we go into the application layer and talk about some of the resources. So what we were talking about before is the architecture, general overview of what's going on under the hood. But most of the time we're not under the hood, we're interacting with it, we've installed it, we've got it up, and so now we want to figure out how to deploy things onto it. The most atomic resource in Kubernetes is a pod. This is an example of any service. So it's a bundle of containers that are always going to be spun up on the same machine. They're always going to have access to each other. So you can specify a service as being one container, or if there are multiple containers that you always want deployed together, you can add them to a pod. This is an example of the configuration. Configuration is really simple for Kubernetes, which is great. It's all in YAML, so it's just kind of these nested hash key value stores. It's really easy to read. Here we see that we're specifying the API version, we're specifying that we have a pod, with a name, a label, and then we reference the image of the container that we want to spin up, which in this case is BusyBox. In addition to pods, we have services. This is kind of the network level for Kubernetes. So services are going to define the ways in which containers talk to each other, how they're available. This is an example of a load balancer, so if that gives you an idea. You're going to specify you have several images running in several containers running in your cluster, and you want anything that talks to them to be able just to refer to my service and have that redirected to one of the containers that's there supporting this application. So it can handle load balancing, and it can handle DNS as well. I was unaware that PowerPoint was a memory-intensive application.
You have to turn off some of your Docker containers.
You're joking, but I think that's actually probably. Oh man, yeah, okay. All right, we're just gonna do this. Okay. You can read it from here, right? So another step here, we have replica sets. So this is typically, you're not dealing directly with pods. You don't want to specify. Does it not have images on here? Okay, we got one of this one. I think I'm missing an image here of an example of a replica set, but it's okay because we got something on the next slide. Replica sets are when you want to specify not just a pod and what image to use, but if you want to specify many of these things that are going to be running in parallel. And replica sets are important because between replica sets and pods, on top of both of those, you have deployments. So deployments will specify basically all of those things packaged together. You have a container specification down here, you have a replica set specification here, and the deployment will handle deploying those pods, managing the replica sets, and deployments actually didn't exist originally, it was just replica sets. So you just want to handle, you know what you want, just put up, I want 3 of this web service, so just spin it up. Now the issue with that was that if you want to deploy new things, it becomes a little tricky. You can't just switch the container that's defined in the replica set. not how it works. So if you want to be able to do something like a rolling deploy, you need a little bit more complexity. And so deployments will handle something like that. And out of the box, the default configuration for if you want to deploy a new set of applications is a rolling deployment. And what this will do behind the scenes is when a deployment sees that it's been edited to have a new container type, it'll actually create a new replica set, and it will scale down the existing replica set to 0. And while it's scaling it down, it will scale up the new replica set to be the old number. And so while that's happening, the service is still pointing to these metadata tags. So all the traffic is still being routed to both sets of containers in that intermediary period. But you're kind of getting a slow replacement one by one of the existing nodes that are in the cluster.
So that's how it stays running, stays up.
Yes, so zero downtime. Yeah.
Cool.
Okay, so how do we actually interact with the cluster? Typically there's only really 2 ways you're going to do it. Primarily you're going to be using kubectl. And I have a few examples of just basic commands here to show you that this is mostly what you're going to be doing when you're interacting with your Kubernetes cluster to see if everything is up and running. You're going to be doing get pods, show me all my pods, get services, show me everything that's mapping. I can do get deployments, get replica sets if I want to look at that kind of stuff. And then when you want to create and delete resources, you're going to just be pointing create or delete to a YAML file. So you wouldn't be typically running like specifying all of the different arguments in there. You would have a YAML file that specifies everything and you would just point to that file. Another thing you can do is scale things up and down via the command line. The other common way to interact with the Kubernetes cluster is via the dashboard. So every cluster comes with a UI. You do have to activate it, but I don't know why you would want to do that. And this will list things like all the different services that you have, all the workloads that you have going on, and it will even show you common metrics like CPU usage, memory pressure, these kinds of things, so you can get a visual representation of what's going on in your cluster. And then jump into some of the tooling. So again, once we have all of these services, we've decided that we like Docker, so we're going to move from being on a single machine and now we're going to deploy it onto a cluster. How do we handle that? How do we handle deploying not just one, you have a deployment that might define one service, your web server, but maybe you have databases, maybe you have other web servers microservices that are interacting with that. How do you deploy all of these things at once? How do you do package management for a cluster of several different applications? And how do we package together sets of microservices instead of just being like one file that defines maybe a deployment for one thing? And now we come into Helm. Helm is a package manager for Kubernetes. It allows you to put together packages that specify the versions of everything that you need. You can link out to dependencies for other packages as well. And it's a pretty simple tool to use. All you need to do is to install it, is install Tiller, which runs on the control layer of the cluster, in addition to like the API server. And the Helm CLI will interact directly with Tiller in order to deploy everything that you're launching through the packages. So what is a package called in Helm? They're referred to as charts. We have a nautical theme going on here. And so it's actually fairly simple in order to package all these things together. This is the top level structure of a chart. It'll specify, you'll have an example of your top level directory, and you'll have a chart that defines like basic versioning, things like that, dependencies. And then you'll have the default values of the configuration that you want to use in this chart. You can optionally have a schema that you use to define what those values, shape that those values have to fit. And then you'll have charts that you depend on, and these will be like zipped other charts, just as gzipped in with this guy. And then templates, which is the actual where the meat of the package lies. Here's an example of a package, and you can see what's inside the templates folder. And you can see it's just a bunch of services and resources. And so you put all these together, and then you can package them in as a chart and deploy them all in one command with Helm. I wanted to talk a little more about networking. I know we covered it a little at the beginning, but specifically Istio, I found was probably one of the more interesting of those tools that's around. It runs on Envoy, which is an additional sidecar, and it provides some of the service discovery stuff is difficult to set up in Kubernetes, but Istio kind of provides it to you out of the box. It gives you a lot of the more complex routing rules for service mesh capabilities, and it even lets you do host-specific routing, inter-cluster failover. So what we were talking about before, if you want to route services, you want to route some of the traffic from one cluster in one place to a cluster in another place, and even this cool topic that I was reading about network shadowing. I haven't used it personally. But what you can do is you can set up a development environment, and you can have it shadow your production environment, and then any requests that are coming into your production environment, they'll be duplicated and copied in and thrown into your development environment, so you can test what will happen if it gets production-like traffic in your staging environment, and figure out, debug anything that might go on there. Another piece that's a little more complex to deal with when you're dealing with multiple machines is metrics and log aggregation. So there's several tools, again, that you kind of take your pick of what you want to use for when you're deploying a cluster. These three are all pretty much come out of the box with Kubernetes. They're very common, and the differences are kind of more nuanced. So Fluentd is a Ruby library primarily that can kind of handle all of your filtering rules and things like that. So the nuances of what's different in here is primarily just different like filtering rules and things like that. The main one that's slightly different is Prometheus. Prometheus is technically not really a logging tool. Logging is more like handling streams of information. Prometheus will actually periodically monitor, but what it will do is it will scrape the logs. So you end up with the full logs of everything that happened. It's just rather than it being a push into the logging service, Prometheus actually reaches out and periodically scrapes the logs and gets everything so it's up to date.
Is one more efficient or than the other? Or
it's just different. So these ones which are piping logs in, streaming, you'll have the data real time. So you'll have it when it happens, but it's also a lot more compute heavy. Obviously, you're having to process these logs in real time, as opposed to if you don't need to have that. If there isn't a business reason why you need to be getting real-time logs, it's better to use Prometheus because it's not going to create as much load on the CPU because you're not going to be constantly dumping these logs. You're just periodically grabbing them.
So if you're expecting to fail at some amount of time, then yeah, okay, I get it.
And then lastly, tools around data visualization. So these are kind of paired with these logging tools. When you want to scrape the logs, you want to set up filtering to alert you, but you also want to be able to go in and see a visualization of your cluster. It's not on one machine anymore, so you can't just go in and see the logs in one place. You want to see, okay, statistics across my entire cluster. How is the memory pressure doing? How often are my services restarting and things like that. So these tools are really useful. And all of this is, you are going to plug this into a Kubernetes cluster. When you're setting up a cluster, you want to have one of these for all of these different things. You got to pick which one you want, but you do need one. And that's it. That's all I got.
To Grafana?
Yeah, so these different tools, they're all, they're meant to kind of, so let me think how to phrase it. Grafana, or Kibana is actually part of the Elk stack, so it's made by the same company as Logstash. So the level of integration there is much higher.
Yeah.
So it's just up to you. There's going to be a little more configuration, but you can set these things up to talk to each other. Yeah, because I mean, at the end of the day, it's just log data. So you might have to do a little more configuration to get them set up, and that's probably going to end up determining what decision you end up making.
Exactly.
If it's plug and play, you probably just want to use the one that's plug and play. Because, like, for instance, if you look at these things, I mean, they're really not that different. These are, user-defined dashboards, and this is a dark theme and that's a light theme. So, you can kind of tell the difference. But for the most part, you can create these things in here, and you can create these things in here. They're just, different tools that are competing in the space.
So one tip that I have, I actually recently, 2 days ago, I configured Grafana on my Kubernetes cluster. So I think here's a tip, like you want to start, like there are these manifests, Kubernetes manifests that is widely available out there. So what I did was that I actually downloaded, so when you spin up a GKE cluster on Google Cloud, you can go into the application page to install a Grafana deployment in your Kubernetes cluster. So you use that as a baseline. So you get something working. Grafana is really simple because out of the box, it has SQLite support. So as soon as you point it to a data source, which can be your CloudWatch, Stackdriver, Prometheus, etc., you have data coming in. You can set up your visualization. And then once you have this set up, then you go into your manifest and start tweaking it. And because it's Kubernetes, you just delete the previous deployment and then redeploy it, and then just keep tweaking until it gets to the state that you want. Save it, so you would like do a commit to your GitHub or your Git, and then you have like all your Kubernetes YAML file, and then once you're ready, you can migrate to Helm, and Helm is like Docker Compose is to Docker as Helm is to Kubernetes. So just like you have all these different manifest files, it gets pretty gnarly to manage all of them. So with Helm, it actually helps you with that. But then you first want to have a solid set of manifest file before you move to chart. So that's how I would configure it. Try it out with something pretty simple, out of the box from some public repo or from the cloud providers, and then just start tweaking it. So
I think the big takeaway with Kubernetes is it's really complex, and there's a lot of customization you can do. So you want to start with something that's going to work out of the box. Find an example of something that you can deploy that's already there, that works, and start tweaking something that's existing, as opposed to try to like ground up, make your own customized cluster before you understand how a lot of this stuff works.
I had a question about the rolling deployments. How does Kubernetes manage, or this whole control plane manage, like versioning of containers and versioning of deployments? Like, is it just checking the deployment file and then it tears down everything in the deployment and redeploys like new containers, or does it say notice that some containers are the same as they were in the previous deployment, so it doesn't tear those down and only spins up new ones that are changed? I'm just wondering the granularity of that.
Yeah, you lost me a little bit at the end there.
Oh, sorry. I guess maybe I'm using the wrong terminology. It sounds like a deployment is a collection of containers,
yes.
Right? So when you change a deployment for Kubernetes, you said that it can recognize that and then start tearing down old containers and spinning up new ones.
Yeah, so it does check like it's what you have specified in the deployment is the image. So like if you change this, like in Nginx, you want to do Nginx 1.8, for example, that's when it would recognize, okay, this container is actually no longer relevant, and we need to add a new replica set with the new container defined here, and this is all going to be stored in etcd, and then it's going to kind of power down these containers one by one and spin up the new ones with the appropriate version.
Okay, so what happens if you have other images or other containers rather, that aren't changing? Say it has like a 1 point, like something upgrades and then something stays the same. Does it also tear down the ones that stay the same? Is that even possible? I don't know, maybe it's
Or within the pod?
Yeah, because a pod can have multiple containers in it.
Yeah, I think it's probably going to tear down everything in the pod.
Yeah, I think it would. I was just wondering if it has any sort of, because for big pods or I guess deployments, maybe that's not.
You try to keep
efficient.
your pods. You try to keep your pods small.
Okay.
Because the problem with pods is that they're by definition going to be co-located. So anytime you deploy a pod onto a machine, it has to have an instance of every single container in that pod. And so if you have really large pods, you can't actually leverage the fact that you have like multiple machines. Like the main reason you'd want to separate your services out into multiple images in the first place is so that you can spin up some over here on this machine and some over on other machines and kind of fan out the load across all those different ones. But if you put them all in the same pod, then they have to all be on the same node, and you're basically not using, you're not load balancing across those services.
Kubernetes upgrade, are didn't hear you say, I mean, like, how would you compare it with all what you talked about today?
Sorry, what was the question?
Operators, so you heard about Kubernetes operators, it's called like operators. Operators?
Yeah,
Operators, yeah.
Not sure I understand the question.
Oh, yeah.
Sorry.
That's why.
Do you work with OpenShift at all? Or
No, I
Rancher?
haven't done any OpenShift stuff. I know there's supposed to be support for that, but it's one of those things that changes a lot over time. So,
Or K3s? You work with those?
no, I've only really done Kubernetes on public clouds. So,
Just curious, who here uses Kubernetes at work?
yeah.
How do you guys like it?
I was okay.
Uniform way to manage like large
Thanks,
projects.
guys.